So remember what we're trying to do. I introduced this model swimmer, model treadmilling swimmer. It's circular and doesn't change shape, but it's got some distinguished direction that's marked on it. That's going to be at some angle to the positive x-axis in an xy plane. And relative to this, we put some treadmilling activity. So something is happening on the boundary of the swimmer to cause a flow. And I actually took this case. I think it was 2. This is the velocity, the tangential velocity sine phi minus theta. So from this angle is phi, this angle is theta. Then I've got sine of phi minus theta plus a little bit of sine of 2 phi minus theta. Okay? And you can see that in principle, I can add multiples of 3, 4, 5, the higher Fourier modes. And I can even put cosine. Up to me. Okay? So this was the tangential velocity. Tangential slip. And I actually set, u is equal to 0. I didn't have to do that. I did, because in that case, the swimmer doesn't, if the swimmer is situated in free space, it doesn't move. Okay, I could keep this in, and then the analysis is the same. Different, but the steps are the same. And what we found, that the swimmer is equivalent to a point stresslet. Let's call this Z naught, center, of strength mu equals e to, well, there's a v there, but I set it equal to 1. Theta at Z naught. And a source quadrupole. Strength, I think it was 2 mu epsilon squared. Where epsilon is basically some parameter that you can think of as the radius. Okay, the reason I set, there's a v sitting here, but I set it equal to 1, because remember, if u is 0, this is the only thing that's driving any flow. So that's just setting the time scale for the motion. So let me set it equal to 1, and set v equal to 1, and then that's setting the time scale of the motion. Okay, and epsilon is just a real parameter. So my model swimmer then, instead of thinking of it as this circular swimmer with a treadmilling action, I'm going to think of it as a point stresslet plus a source quadrupole. And in free space, there's no difference. The flow generated by a stresslet and a source quadrupole is exactly the same outside the cylinder as the treadmilling. And then, my approximation then, so how does such a swimmer move near a wall? Well, that's not actually the question that we answered on Tuesday. You see, to answer that question, I've actually got to look at this little swimmer, near this wall. this is Z naught here. Okay, this is what I actually need to solve if I need to answer this question. Last time, I didn't answer that question. We approximated the answer. So as an approximation of the answer, we studied this last time. It's the same wall, but we're not going to think of we're going to replace the swimmer by the stresslet plus quadrupole. It's a point stresslet. Plus quadrupole. Okay. And that's the problem that we solved last time. You remember I did all of those things where I know what f and g prime, the kind of singularities they need to have here, and then I found the image system here using the no-slip condition, an analytic continuation. Remember? And I was able to produce, this produces a system of ODEs, or a dynamical system. But this is really what we have to study if we wanted to answer that question. And so the question remains, this is an approximation to this problem, but how good is it? So the question is, how good is this point swimmer approximation? And that's the question that I want to answer for the first half an hour or so. Let's call this problem 1. This is the problem we actually care about. What does this actual treadmiller do near the wall? I've got an approximation of what I think it will do near a wall. It's an approximation. Because I've approximated the swimmer by this particular set of singularities. But let me see if I can answer this question exactly. And I'm going to do that using a very clever trick that is good to know anyway, because lots of people use this. I'm going to consider two problems now, problem 1 and then problem 2, which is going to be in exactly the same domain. So this is problem 2. But now, this isn't a swimmer. It's exactly the same geometry. This is still a swimmer of the circular disk of the same size and the same position. But now this is a solid cylinder. This is our swimmer. But the domains are identical. So this is D and this is D. Everyone think about this, because I remember when I first came across this, I learnt this when I was a student, but I remember I didn't really realize what I was doing. But So there's two different Stokes flow problems, but the geometry is exactly the same. What's the difference between the two problems?
The boundary conditions.
Must be the boundary conditions. If these are two different Stokes flow problems, but the geometry is exactly the same, the only possible difference can be the boundary conditions I'm taking. So, let's make the boundary conditions on the wall the same. So this is a no-slip wall. And this one's a no-slip wall. But on the swimmer, it's going to be moving at some velocity and rotating at some velocity, and it will also have the treadmilling action. But the solid cylinder, oh, and of course, there'll be no force and no torque. Those two conditions will determine the speed and velocity of the swimmer. Now, in contrast, what I'm going to do with the solid cylinder doesn't have any cilia or any mechanism on the boundary to produce a treadmilling action. So it's only going to possibly move or rotate. And it will only do so if I exert some forces and torques on it. Okay? So those are the two different problems. They take place in the same domain, but the different boundary conditions on the cylinder. Okay, so keep this in mind when I tell you about what's called the Reciprocal Theorem of Stokes flow, which I'll do over here. So bear that in mind. So this is for Stokes flow. By the way, for your general education, I've put for Stokes flow here because these reciprocal theorems exist in other areas. In plane elasticity, solid mechanics, it's known as the Betti reciprocal theorem. That's in solid mechanics, B-E-T-T-I. But the idea is essentially the same. Okay, so by the way, this mu here is the viscosity. It's not the mu over there, but remember, I've taken the viscosity to be 1 all through these lectures. So I put it there in case you're wondering about it, but it's in principle sitting there, but I've set it equal to 1. This is known as the rate of strain tensor. And if you put it in this combination here, sigma is known as the stress tensor. Okay? What do we know about sigma ij, the divergence, if you like? Or basically the contraction with derivative xj. Oh, and by the way, I'm going to insist that div u, this is equivalent to div u in index notation. Div u is 0. But if you think about it, if the Stokes equations hold, this thing is 0. If and only if the Stokes equations hold. You can see this just becomes the gradient of p basically, and this one basically becomes del squared u. So what you get is 0 is minus grad p plus del squared u. Those are the Stokes equations. So just exercise, that's just a little vector calculus check. Exercise is one line. Check this. Vector calculus. You have to use this. Okay? So the Stokes equations can be written as follows. D sigma ij by dxj is 0, and du, let's call it j. duj by dxj is 0. It's just a different way to write the same equations. Okay, so what we're going to do is consider two different Stokes flows in the same domain, D. So in your mind, you can be thinking of problem 1 and problem 2, where D is this region, fluid region here. Two different problems. Okay? We'll call the solutions sigma ij uj, and the same things but with primes. For example, this could be the solution to problem 1, this could be the solution to problem 2. Okay. So consider the following. Let's take d by dxj It seems like a strange object. You'll see why it's useful at the moment. What I've done is I've taken the velocity field from one problem, multiplied it by contracted it with the stress tensor from the other problem. Very strange thing to do. Think about it, it's very strange. You've got two completely different problems and somehow you're contracting something from one solution with another one. Very strange. But we'll see how useful it is. So we've got these two, and then we take this x derivative, and then we're going to subtract the same thing, but with the opposite, u prime with sigma. Okay? Let's just expand this out. So we get ui by the xj. Please watch me so I don't make any mistakes. This is the product rule. Okay, that's the first one. I'm going to subtract, what is it? The ui prime by the xj sigma ij minus ui prime d sigma ij by the xj. That's just the product rule. What do you notice about these? This one and this one. Well, they're 0 because these are solutions to the Stokes equations. So that one's 0 and that one's 0 because of this. Remember, let me just emphasize, this is true with primes as well because there's two solutions. Okay. One more take a look at the sigma ij. You notice any special properties of it? It's symmetric, isn't it? If I swap I and j, I get the same thing. This is just the isotropic tensor, which is clearly symmetric, and then that's Eij, which is clearly symmetric. Okay? So notice that sigma ji is sigma ij. So let's see what, so let me put it this way. Look what I can do with this. I can take half of this and add it to half of itself. Right? I'm going to add the same thing again, but I'm just going to rename the indices because it's a contraction on two indices. Everybody see what I've done? This is a double contraction. I've just changed I to j and j to I. So this is the same as this, and so if I add two of them and divide by 2, I've got that. And I'm going to do the same here. Okay, I could just add the same thing, and I am, but I'm going to swap I and j. But now, by the symmetry of these things, this is the same as sigma ij prime. So, and that appears there as well. These are different. But this is the same as this. And this is the same as this, by this symmetry. So let me take that outside. Everybody with me so far? What's this? Yes, that's Eij. And this one's Eij prime. So I've got everyone happy? Now, let me use the definition of sigma ij. Which is that, right? For sigma ij prime, where P prime is the pressure from that tensor. And then now look, you've got Eij contracted with Eij prime. But then you've got the same thing here with the opposite sign. So they clearly cancel. And then what's delta ij Eij? Well, that's just Eii, which is div u, which is 0. Isn't it beautiful? See, so this is basically minus P prime Eii plus P Eii, which is 0. because dui by dxi. Similarly for and prime. Everybody see? It's kind of amazing, isn't it? I'm using lots of facts here. I'm using the symmetry of the stress tensor and its definition, of course, and then the incompressibility is crucial. But the difference of, where did we start? This minus this is 0. By the way, I'm not too sure of the history of this, but I think it's, I know this is something called the Lorentz Reciprocal Theorem. So I think it was Lorentz who spotted this, I'm assuming, the first time. I don't know the history, but my guess. What do you think I'm going to do now? Look, I've got basically a gradient operator here, and these are purely local statements. But I've insisted that both flows take place in the same domain. So I'm going to make this a global statement now by integrating this over the domain. Okay, so where do I want to go? Let me just do it again. So this is the conclusion. Oh, let's not integrate yet. Let me just say the conclusion. D by dx j of u I sigma ij prime minus d by dx j is equal to 0. So let's now integrate over d. This is a volume, area integral in 2D. By the way, everything I've done here pertains to 3D as well. Just so you know, that I'm thinking of this for this two-dimensional application, but it works in 3D as well. So let me do it here. I don't want to erase those. Actually, maybe I will. I'll draw them again. Okay, so the integral over d call it dA because it's an area integral of 0. What does everybody want to do to the left-hand side? You want to use the divergence theorem, because you've got the integral of a gradient. So by the divergence theorem, let's turn it to an integral around the boundary. This becomes an integral around the boundary of D of ui sigma ij prime nj ds, where ds is the little arc, for 2 dimensions, it's just the little arc element. And I'm going to move the other one over the other side. And that's it. That's the statement of the reciprocal theorem. Does it remind you of anything? Have you seen anything like that before? You actually have. Although I'm sure you have. I only realized this much later, but have you ever heard of, you've heard of Green's identities, where you do things like, you think about things like this. These kind of operators, which is the same as if it's these are harmonic fields. Really, this is if I like to think of the reciprocal theorem as a biharmonic generalization of Green's identity. Because if you integrate Green's identity over the domain, you end up with a similar relationship between two harmonic fields in the domain. Okay, so this is like, I like to think of it as the biharmonic or Stokes flow analog of Green's identity. Any questions? All right. How am I going to show? Okay, let's go to our, let's apply it. Let's use it. Remember, I'm going to draw my pictures bigger now. So here's my swimmer problem. Should we call this the swimmer problem? Let's do this. This is the, no, we might as well keep the same notation. This is my swimmer. Right, let me just indicate the little treadmilling. And the whole point is, this is moving at some speed u, and possibly rotating at some angular velocity sigma s, omega s. But the forces and torques are 0. Let's call this ui prime sigma ij prime. That's the solution. And actually, for no, it's okay. And here's so that's problem 2, problem 1. And then here's a completely different problem. The cylinder. The whole point is, this is moving at some, let me draw a different arrow so you don't think it's the same. And I'm going to suppose that there is a force and a torque on that one. Otherwise, I can't see how it's going to move. So let's suppose it's got some, well, it's the only force around, so let's just call it F, and there's maybe some torque T. Okay, so this is like you've got a wall, and you've got honey above the wall, and you're dragging the cylinder through the honey. And it's going to be hard work because the honey on the wall can't move. Let's call this the dragging problem. Okay, this is problem 2. Oh, and this has got solutions ui sigma ij. And this is D. And that's D. Let's introduce the underlying sigma s and call this 0, 0 f theta s. And Same thing here. These are definitions of the underlined. What's the boundary condition on the swimmer here? Let's call it C. So this is C. And this is also C. And I'm going to ask the same question about this one. And I mean vector notation here, not complex. Well, let's do this one first. This is a cylinder that's a solid body. So it can only move with Euclidean motions. You know, it can translate or it can rotate. So the velocity, I've told you, its translational velocity is ud, but it can also rotate. Okay? So I can write in vector notation as, what is it, x, let's call the center of it x naught, x minus x naught cross omega d. Solid body rotate, or the other, maybe the other way around, is it? It doesn't matter, it will just mean the sign of that changes. Okay, this is a point on the boundary and it's rotating about that point with some solid body, with some constant angular velocity, so it's omega cross d. And that's it. That's the velocity on the boundary. But here, it's moving with speed us, with possibly but also some treadmilling that I'm imposing. So let's call that ut. This is the treadmilling action. So this is just the displacement velocities. This just displaces. There's no treadmilling. You okay? By the way, I'm not even going to insist that it's tangential here. Just some extra velocity on the boundary that comes from some process. What does the reciprocal theorem tell me? Well, here it is. And the whole point is, this has got to be around all of the boundary components. So we've got the lower wall and C. But you'll notice, because I've insisted that both problems have no slip on the wall, because the U appears here for both problems, there's no contribution from the wall. So what it says there is that if you go around C then, you get that. So there's no contribution from the wall, so I can replace delta D by C. Does anybody mind if I now go to contract just dots and stuff? So this is equivalent to u dot sigma dot n ds. It's just, I'm just moving to a standard vector calculus. You see, I'm just changing. I don't want to write it in index notation anymore. I want the velocities because I've got these expressions here for the u's. Oh, I need to put a prime on here, don't I? Because everything is prime. Let's substitute the u's. And this is where the magic happens. Let's substitute the u, which is this one. Okay, I've just substituted u from this one, and I'm going to substitute u prime from this one. Let's look at the left. Everyone see what I just substituted for the u? Here and here. And look, these are constant vectors. So I can take them outside the integrals. So this is, let's just look at this one. This is ud dotted, as that dot, with the integral around c of sigma plus omega d cross the integral around c, running out of space, of x minus x naught oh, okay, no, we've done that already. No. Okay, this is a little exercise for you. You can see that you can basically swap these around. That's a little, if you put it in index notation, it's very clear. That's just a little exercise, just moving from this one to this one. Just showing that you can basically swap these two around. Everyone see, all I've done is I've taken constant vectors outside the integrals. Now what's this thing? Everybody pay close attention because this is the beautiful, we're nearly finished. What's the thing in red? What we say? The net force. You see, remember, sigma is the stress tensor, so if you dot it with n and integrate around the boundary, it's the net force on the boundary in the primed problem. Which is which problem? The swimmer problem, where we've insisted that the net force is 0. And what's this thing? Well, there's your little force vector on the boundary, and you're crossing it with the distance from the center. So that's and then you're summing up. That's the total torque. You want to see? So the left-hand side is 0. Okay, so this is 0 because it's force-free, and 0 because it's torque-free. we've nearly finished. We've just concluded hold on, let's not finish yet. Let's carry on. No, let's write one more line. So 0 then, we just decided, is, and I'm going to do the same on the right-hand side now. So I'm going to take those constant vectors out. Remember, I can swap these things around. I just did on the right-hand side exactly what I did on the left-hand side for these two terms, and then I left this one alone. There's nothing I can do with that, because remember, the treadmilling on the boundary is not constant. It's a function of space. So that's some function you give me. Well, what's this? It's the same thing as before, but now for the unprimed problem, that's just the force on the cylinder. And then what's this? The torque on the cylinder. And remember, this is only going to have a component in the third component, as does this. So when you take the dot product, you just get the product of sigma s without the underscore with the torque. So plus sigma s times the torque. And let me move that on the other side. Oh, sorry, I forgot the US. Okay, we'll stop for a few minutes in a minute, but let's just look at this. Anybody got any thoughts? Have a think about this. How on earth, what I'm going to claim is that I can use this to get the swimmer velocities without solving the swimmer problem. So think about that. That's very important. It's not very often in mathematics that you get to determine something from the problem, but without solving the original problem, but by solving a different problem. Here's what I mean. What we're looking for is this and this. So, and remember our problem. We've got a little treadmiller, and we're imposing some ut, this treadmilling action, and insisting that it's force and torque free, and then it will move somehow. What this equation says is if you take a solution of the dragging problem, which means that I will know this thing, because there's no primes on that, I will know this thing, and I will know this thing, and I know this because that's what I'm specifying, which means I know the whole of the right-hand side, I know this, and I know this, then it gives me a linear equation for the US and omega s. Does everybody see? It's amazing, isn't it? I'm going to fix the treadmilling action. I'm going to take a solution of the dragging problem, which means I will know this thing, I'll know this, and I'll know this. This is then a linear equation for relating us and omega s. Now, this is one scalar equation. Everything's scalar. How many unknowns do I have? How many real unknowns? Scalar unknowns. 1, 2, 3. So I'm going to need 3 equations. But I can just take 3 different solutions of the dragging problem and generate 3 equations. Does everybody see? For any solution of the dragging problem, the reciprocal theorem gives me a linear equation for the things I'm looking for. So if I take 3 different solutions of the dragging problem, use this, I'll get 3 equations for the thing I'm looking for. And all without solving the flow for the swimmer. It's amazing, isn't it?
Some sort of independence.
Yeah, you see, I mean, intuitively, if I put the same solution in 3 times, I'm going to get the same equation. But if I take 3 different solutions, for example, you see, the most natural thing to do is to take a solution where there's no force and a torque. Then it's explicit. And then perhaps with just an x component of force but no torque, and then a y component. Let me find those solutions, and then I'll be done. Okay? Right, we're going to stop for 5 minutes, but there's just one problem, of course. What the hell is the solution of the dragging problem? I'll tell you in 5 minutes. But please stare at this, because people use this all the time in microfluidics, colloid science, low-Reynolds-number swimming, biomechanics, because they happen to know something about the solution of the dragging problem. Think of that as a treadmiller. Except certain parts is moving. It's kind of what do you call it? Some parts can move faster than others, like a caterpillar. But the whole point is it's a fixed surface, because you know it's a flat surface. When your luggage comes out, it's still flat, but there's a belt that goes round at some speed. That's what you should think of, because if it's on the surface of a swimmer, it's generating a flow around it. Because remember, it's a viscous fluid. So if the surface is moving, the fluid gets dragged with it. So remember, if you're in ideal flow, suppose I had a cylinder in ideal flow and I just rotated it, nothing would happen. Because it slips. If I've got a cylinder and I rotate it, or I don't even rotate it, but I've got a little surface that goes round, like a belt, it will drag the fluid with it. And so this is allowing me to have a kind of dragging of all kinds around the cylinder. Allowing me, by the way, to capture lots and lots of different physics. Because, by the way, in most applications, I'm making this up here. Remember, I put it sine phi minus theta plus sine 2 phi minus theta. I made it up. In most problems, and I've solved some problems like this too, it comes out of another problem. So, for example, you might have an electric field. Your swimmer might be some dielectric particle or something, and you've got electric field around it, and then the slip velocity, or the treadmilling, is some function of that electric field. This brings me to another point. You see, I left you with the thought, this is useful if I know the solution of the dragging problem. Now, suppose I still had to solve that dragging problem numerically. Then I've still gained. Why? Even if, you see, you might ask yourself, well, if I've got to solve the solution of the dragging problem numerically, why don't I just solve the original swimmer problem numerically? So, why are you bothering with all this? There is still advantage in this. Can you see why? You can? What would you say? More than that. You see, I don't actually see much difference in boundary conditions here. It's this velocity or that velocity. So numerically, they look the same. Pretty much. I don't care if it's this or that. But think about it. I can give you any treadmilling velocity I like. Depending on which application I'm solving, I can just change my mind. Which means, if I did not use this, I'm going to have to resolve the problem for every different choice. One day I might say cos 2 theta plus 5, 10 times cos 5 theta around the boundary. Or next day I could choose something else. But suppose that I'd numerically determined, and I'd stored all the data, for 3 solutions of the dragging problem. Can you see why that's more valuable? Because now, you give me whatever UT you like. I know this, I've stored the data. I know this, I've stored the data. I know this, I've stored the data. So now I can just plug in whatever you give me, and all I've got to do is an integral. That's much cheaper, isn't it, than resolving the whole boundary integral set every single time you give me a different UT. See, so there's advantage even if you have to solve the dragging problem. Even if you have to find this numerically, this is still useful. Everybody understand? Now, this is the beautiful thing for me. Because I've told you the story that when Yizar Orr, my collaborator, first asked me about this, I replaced the circular treadmiller with a point singularity and solved that problem, the approximation. But then a year later, I kicked myself because I knew that this was true, but I'd completely forgotten that the solution to the dragging problem in this geometry is known in explicit form. Exact solution, found in 1981 by Onishi. David Jeffrey and Onishi, who I think is still around. He's moved into a different sphere now, but he's still, I think, here in Japan. 1981, Quarterly Journal of Mechanics and Applied Mathematics. They solved it using bipolar coordinates. Anybody heard of those? Anyway, can you see why I was kicking myself? Because I knew the reciprocal theorem. I'd forgotten that the solution to this problem was known analytically, so you don't even have to solve it numerically, which means that I can find this solution, the swimmer velocities, by just doing these integrals with no approximation at all. Does everybody understand? And of course, I wrote another paper where I did the actual exact solution, and I'll show you the results in a minute. But what I thought I'd do is to test our understanding of complex analysis for Stokes flows we're going to spend 20 minutes re-deriving Jeffrey-Onishi solution using our methods. F and G. They didn't do that. They found psi using some bipolar changes of coordinates and things like that. We're not going to do that. So let's find, we're going to use this, but let's find the solution of the dragging problem. Okay. So here we go. We've got this problem now. And let's put forces and torques in a different color. So what is the flow generated by a cylinder translating near a wall with speed u and rotating with angular velocity omega? That's the question. Okay. Okay, this is going to be fun because we'll see if you learn anything. How do you think, so first of all, what have we got to find? We want to find the flow around the cylinder when it's moving with speed u and some angular velocity omega near a wall. So we need to find, aim, find f of z and g of z, or g prime of z, analytic in D, such that the wall is no slip. And what's going on in the cylinder? What's U plus IV? What's the velocity of the fluid on the boundary of the cylinder, which is moving with speed u and rotating with angular velocity omega? Well, remember, on a any solid surface is a no-slip surface. so that the fluid velocity has got to equal the velocity of the boundary at every point. And the velocity of the boundary is u, and is it, let's see, right? Well, it's obviously u. That's a complex, by the way, this is complex speed. Oh. Okay, I've put forces. We're not dealing with forces at all. We're going to solve the boundary value problem given the velocities. And let's see, we need to work out what the rotation is in complex notation. So I'm just going to think out loud over here. If something's in solid body rotation, then omega is 2 omega. Is that right? And remember, this is minus 4 psi z bar, because it's minus del squared psi. Okay? So, yes. So let's think about this then. This implies that psi z, integrating with respect to z bar, is, I got this right. Anyway, right, and then u minus iv is 2I d psi by dz, which is minus I omega z bar. The vorticity is always twice the angular velocity. And remember, the vorticity is minus del squared psi, which in complex notation is minus 4, remember the 4, d by dz by d by dz bar. And now what I've done is this is constant, so what I've done is I've integrated this up with respect to z bar to give me psi z. And I've not added an analytic function here because it's pure solid body rotation, there's no strain. And now u minus iv is 2I d psi by dz in identity, and psi z is this, so I've multiplied this by 2I, giving me minus I omega z bar. So u minus iv for solid body rotation is minus I omega z bar. So u, which is anti-analytic, by the way, which is great because this is in irrotational flow, which this isn't because it's rotating. This is a dw by dz analytic function. So I'm very happy to see a completely anti-analytic function here because it's rotating. So u plus iv is I omega z. That's what I need here. Everybody see how I got that? That's the kind of thing I always have to work out each time because it's you got to get the 2's and the i's and the minuses right. So I think that's right. Except, let's just remember one thing. This is rotating about the center of the cylinder, which is at z naught. Okay. What do you think we should do? That's it. That's what we've got to do. We've got to find two analytic functions, f and g, that are analytic in this region D, such that u plus iv is 0 on here and that thing on there. Well, Jeffrey Onishi used bipolar coordinates. But I don't want to do that. And they didn't use complex analysis. They didn't even find f and g. They found psi directly. What can you tell me? How many people came to my lecture colloquium? Does anybody come to my colloquium? I spoke about multiple connectivity. Can anybody tell me what the connectedness of this domain D is? What's the connectivity? Well, suppose it was just the upper half plane. What's the connectivity of the upper half plane? Simply connected. There are no holes. Connectivity is how many holes is there. Okay? So it's simply connected. But we've got a cylinder in there, which means it's doubly connected. Okay? Here's an idea. Why don't we use conformal mapping? Because I don't know about you, but I wouldn't even know how to conveniently represent a function f, say, that was analytic in this awkward domain. It's a half plane with a hole in it. How do you represent a function? Suppose I wanted to Taylor expand. That's one representation of an analytic function. Which point do I expand about? Do you see the problem? See, suppose I chose to expand in about here, because I know it's analytic outside the thing. That would only converge up to here. So a Lorentz series about the circle center would only converge up to there. But what about all over here? Something else you might think of doing, by the way, is you say, oh, look, there's a infinite line here. Let me use a Fourier transform. But Fourier transforms are only valid in strips of analyticity. And then, by the time you reach the cylinder, that Fourier transform will stop being valid. You see? Have you ever thought about this before? If you've got analytic functions, all those things you learn about in complex analysis, Taylor and Laurent expansions, Fourier transforms, if you've got a difficult geometry like this, they can be used in bits of the domain, but only bits of it. And then you've got to patch them together somehow. I'm going to use a conformal mapping to something simple. Who remembers what the Cayley map is? Do you remember? What is it? To disk. Very good. See, he's been listening. Okay. You remember what it is? Let's do this one. It's this one. I'll check in a minute that I got the sign right. Let me just check. Let's check z is equal to 0. That goes to 1, which is over here. Right? And let's just check that how did I check that the unit circle maps to the imaginary axis? I told you a trick to do that. Always take the conjugate. Remember? So on z is equal to 1, z bar is 1 minus zeta bar over 1 plus zeta bar. That's right. But zeta bar is 1 over zeta. So now remember you multiply up by zeta, and this is minus z. So on this circle, z bar is minus z, which means it's the imaginary axis. The other thing I need to check is that the origin goes to in this right half plane, which is, well, somewhere in the right, because then I know that this shaded region corresponds. Because you see, unless I check that, this could map to this side. That's the Cayley map. So how am I going to map to the, how do I map this to the upper half plane? Go on, Rodri, say it. But how do I do that analytically? I, yes. So then this is going to be, so I'll tell you what, let's call that eta. Eta plane. So z is going to be, and you know what? I can always rescale everything by a real fact. So I want to multiply it by, look, watch everybody. Well, right where r is real. That rotates everything. That's still the Cayley map, anything that maps a disk to a half plane. But it's not the half plane that I'm interested in. I'm interested in this half plane with a disk missing. Here's some, by the way, I might as well tell you all of this. Here's an interesting fact. Fact 1. Cayley map is an example of a more general class of maps. Anybody know what it's a more general, it's a special case of? There's lots of names for these. It's a special example of a Mobius map. A, B, C, D are arbitrary complex constants. This is a Mobius map. Some people call them linear fractional because it's a fraction of two linear. Some people call them bilinear maps. It's another one. I think because there's a linear and a linear, so there's two linear. Okay? But whatever you call it, this is what they are. Here's another fascinating fact. If I think of this as a mapping between two regions, this mapping here, any A, B, C, D, and then I think of, in the zeta plane, I take a circle, and then I put it through this mapping. Do you know what the image will be? What shape it will be?
What's the answer?
Fact, every single circle gets mapped by a Mobius map to another circle. And by the way, you might be wondering, well, what about this Mobius map here? This is still a circle, except it goes through the point at infinity. So straight lines are circles that just have to go through the point of infinity. Isn't that an interesting fact? By the way, just so you're clear, there's lots of other maps that aren't Mobius that will map a particular circle to another circle, a particular one to another one. Lots of functions do that. Mobius maps map every circle to another circle. By the way, there's a little exercise to prove that to yourself. We can use fact number 2 here. See, I'm looking for a convenient way to map this difficult geometry to something more convenient. And I've already done this. I've already mapped the unit disk to this upper half plane. And I did it, by the way, with a Mobius map. Now, I don't have all of this. Unfortunately, I have a circle. There, this is my cylinder. Can you see what this fact helps me deduce? By the way, let's suppose it's centered on the... Let's suppose this is the origin, which, by the way, is this point. And then remember, this goes off to infinity. -1. So, have a think. Let me just ask myself the following question. What does this circle get mapped to? Well, I know my mapping is Mobius. So it gets mapped to a circle from fact 2. Let's suppose this is rho and minus rho. Let's look at this point here. And let's let zeta equal rho here. So I've got 1 minus rho over 1 plus rho. Rho is real. So what's the image point going to be? That's purely imaginary. This is real. By the way, I forgot to, R had to be real here in order for it to look like that. If this is rho, 1 minus rho, 1 plus rho is real, that's purely imaginary. So in other words, it will be on the imaginary axis. So in other words, let's call this point A and B. A is going to be very close to the origin and on the imaginary axis. So this will be the image of A. And then over here, look, I go to minus rho. That's also going to be on the imaginary axis, but further away. Everybody see? So let's see. Z of rho. Let's put some notation here. Look. Let's call this D and the radius S. Radius S. Z of rho must be I D minus S, and Z of minus rho, that point, must be that top point. See, everyone see? And let's just talk like this. Z of rho will be I R So given D and S, I can solve these simultaneous equations for rho and R. I can even tell you the solutions, you can check. Everybody following me? What I've just done is I've found this conformal mapping. Known parameters are given by this. Remember, if rho is given by this in terms of DNS, then this is a function of DNS. I know capital R, and rho tells me, when I solve for rho, it tells me what the conformal modulus is here, what this rho is. And then this mapping takes me from the annulus to my domain D. Now what? Now what should we do? Remember, we're trying to find f of z, g of g prime of z in that difficult domain. But why don't we introduce what I think I've previously called capital F to be f, this is definition, f of z of zeta, where z of zeta is now this thing. I'm thinking of this. I'm abusing notation here because remember, z is a coordinate, but it's also the name of this function. But you understand, it's just that function. And then I've just composed z with f and g. What can you tell me about the analyticity properties of capital F and capital G in the annulus? So we're in this annulus, and then if I go through to z, this function, I'm in here now, and that's an analytic function except at -1. So this point goes off to infinity in over there. But then I compose it with f and g prime. But in my physical problem, what's going to happen to the velocity far away? It's going to decay. Because remember, I'm just dragging this cylinder. The flow far away is going to tend to 0, which means that f and g prime will also tend to 0. In other words, they'll go like 1 over z. So even as zeta tends to -1, z might go off to infinity, but f and g, capital F and capital G at -1 are still going to be fine. There's not going to be a singularity. So f and g are actually analytic. In the annulus. And on its boundary. Now that's good news, because I know how to represent functions that are analytic in the annulus. In a uniform way. Okay? Can anybody tell me, all right, let's try it. So, hence, it is natural to consider Lorentz series in zeta. Okay, let's look at the boundary conditions though. On z is equal to 1, which is this wall, u minus iv, which is minus f of zeta bar, Notice, look what I've done here. Remember, u minus iv is minus f of z bar plus z bar f prime of z plus g prime of z. And f prime of z is f prime of zeta over z prime of zeta by the chain rule. So I've used both of those facts here. And then on the, remember, on the other one, u minus iv, which is minus f, same thing. Is the other thing, that. Except it's u minus iv. I've just used this boundary condition, the no slip on the wall, which is the unit circle, and this condition on the cylinder, which is this row circle. Let me simplify these. Or this is f bar zeta bar. Now, on this circle, zeta bar is 1 over zeta. Same thing there. On this circle, look, I've used the fact that zeta bar is rho squared over zeta. Right? Just look. If I square both of these, this is zeta bar. Oh, sorry. You're probably wondering why I haven't put that there. Sorry. Rho squared. Sorry. But look what I've done. That's very, very important. I've replaced zeta bar everywhere by 1 over zeta on this circle and rho squared over zeta on this circle. Similarly here. So now, in my boundary conditions, there's no longer any barred variables. Which means that I can analytically continue these off those circles. Very, very important. And it's the whole beauty of complex analysis that's encapsulated in statements like that. These two used to be valid just on the circles that they came from, but now they're valid everywhere. They can be continued. Right? Isn't that amazing? So in particular, here's G sitting here in both equations, and they're both valid in common domains of validity, so I can subtract them to get rid of G. So by analytic continuation, so these are valid off the original circles. There's an analytic continuation argument there. So subtract 1 and 2. Or let's subtract 2 from 1. Okay, now I've nearly finished. There's just one more step. This is the big equation for F. F is conjugate. Schwarz conjugate. By the way, the only notice the following remarkable fact. This is let's multiply by zeta top and bottom. This function, it turns out, remember, I know this function because I know the mapping. And I did some calculations earlier, and I'd already done them in my paper anyway, but you can show that this thing, which is in that square bracket, is just this. And this thing is just this. And in particular, notice that they both have the same denominator, zeta plus rho squared. So this and this thing are the only things in here with singularities in terms of the non-F quantities, and they both have the same singularity. So what I'm going to do, you see, I need F analytic in here. Here's a question for you all to see if you've understood. Am I expecting F as I go round this? Remember, the blue circle corresponds to the cylinder. Am I expecting F to come back to the same value if I encircle the cylinder? In other words, am I expecting F to be single valued in the annulus? Think about that. Remember, I told you that the single valuedness of F and G prime are intimately connected with forces. The force is in fact the change of that function capital H I introduced. Am I expecting f to be single valued here? No, because the only way this cylinder is going to move is if I drag it with a force. Right? So I'm not expecting f to be single valued in the annulus. So what I'm going to do is I'm going to let, let's call it FL. I'm going to put a log zeta, which clearly has a branch point at the origin, so it means that if I go around the origin, I'll certainly won't come back to the same value, plus a Lorentz series. Everyone see? And now all you do is you take this. You take these facts, which also appear in this main equation, there. These are known. You substitute the expression in there, and in there. And then what you can do, by the way, is you can integrate, you can multiply up by zeta plus rho squared, and then both sides are just Lorentz series. So substitute multiply up by zeta plus rho squared and equate coefficients. And here's the beautiful fact that is the reason why Geoffrey Onishi found an exact solution. Turns out that only two of these coefficients are non-zero. So it truncates. That's why Geoffrey Onishi found these bipolar exact solutions. What you find is that f of zeta is FL. I won't give you the, it's all in my paper if you want to look them up. And they're not, they're not difficult, but you have to get all the details right. Basically, you find that f has this form, where FL, B, C depend on R, rho, U, omega. If you want to see the details, as I said, this is different from Geoffrey Onishi. So I did it this way. I'll tell you why I did it this way in a second before we stop for a break. If you want to see the details, it's in this. It's the only paper I've ever published in this journal because I was invited to publish there, so that's where it appears. But I give you all these formulas if you want to work out the details. I've just given you a sketch of what I did. But basically, once you've got F, look, where does G come from? Yes, he's looking in the right place. Look, G is that. Put it on the other side. Done. We found F and G, which means we found the flow. If we found F and G, we can find the stress tensor. We can also find the force and the torque. So can everybody see can you see in your head now what I had to do next in my paper? This is the solution of the dragging problem. And remember, I've got that reciprocal theorem result. All I had to do was work out the integrals on the right-hand side. And by the way, the reason that it's a secondary reason, first of all, what I could have done is I could have taken the Geoffrey Onishi solution, worked out all of those integrals. Remember the integrals? On the right-hand side, it was something like the integral round the cylinder of the thing you were, the treadmiller, dotted with sigma dot n. So this will come from f and g that I've just found. Right? Now, if I'd used the Jeffrey-Onishi solution, I'd have been working out these contour integrals in terms of bipolar coordinates, in which, by the way, lots of sinches and coshes and exponentials appear. None of them appear here. And in fact, what it means is that all of these integrals just end up being integrals of rational functions of zeta, which means that I could find them all using the residue theorem very easily. Indeed, if I'd used Jeffrey-Onishi, I'd have gotten lots of cumbersome integrals in terms of sinches, coshes, and exponentials, and you probably would have done a change of variables that's equivalent to this reformulation to be able to evaluate the integrals. All right. Do you understand how I finish this off now? I put f and g to compute this in the reciprocal theorem, and that will tell me the swimmer velocities without approximation. Okay? And I was very pleased to see that when you look at the, you remember the phase portrait for my model? Remember this phase portrait for the model was, there was, remember, this is the y theta thing. There was a steadily translating state, and then I had these little nonlinear periodic orbits. Remember all of this? That's what we saw in the numerical experiments, and then we saw in my approximation, we see exactly the same, slightly different. But what it shows you is that my point singularity approximation is reliable. Right? And remember, there's no approximation here. This is what the treadmiller actually does. Do you understand? By the way, I showed you this because if you've got a circular object, particle, swimmer, near a wall, you can use what I just showed you. All you need is the slip velocity. Okay, let's take a break and then finish up. And there's lots more things I could have told you, but we've got 1 hour left, so I think I'll just give you a flavor of something else, because in the title I put MOFs, microfluidics, and micro-organisms. So we've really only done micro-organisms. Let's just finish by giving you a flavor of microfluidics. If nothing else, I hope I've given you a flavor of lots of problems that you can tackle using complex analysis in Stokes flows where people don't really use complex analysis, unfortunately. But it means there's lots of nice problems to tackle. And the great thing is, all these new technologies are producing new problems all the time. In microfluidics, biomechanics, colloid science, medicine, drug delivery, sperm motility, fertility science, all these things that do with low-Reynolds-number organisms or particle suspensions at low Reynolds numbers. Lots of huge area of investigation. I think I've been through these slides before. Right, so I showed you these earlier, but now you get more of a picture of what these people were doing. It's the same idea. They were approximating a sperm cell with a stresslet and looking at its image system, which you remember from our analysis wasn't just an image stresslet. There was a stresslet plus some other source contributions. Yeah, these. So there's 3 different singularities there. We know how to find them now. These were the experiments we saw, and these different... remember, oh, by the way, I was talking to Curie about this. You see, these were actual spheres with rods, connected by rods, on a plane. So the plane was this, but there was a sphere there and a sphere there. But the point is, it was doing some motion in this plane. So it was a 3-dimensional problem. But we managed to assess and quantify and see, rationalize that planar dynamics within a 2-dimensional model and learned some important things. For example, what wasn't clear from this calculation was that actually it's the quadrupole that makes all of the difference. If you just had a, remember my swimmer was a stresslet plus a source quadrupole. Most people don't include the quadrupole. But if you just have a stresslet, all it does is it crashes into the wall, which is not what this is doing. So what I learned from the Treadmiller model is that it was the quadrupole that, in a sense, rectifies the dynamics. It's the quadrupole contribution. Oh, remember these graphs? You know, with the steadily translating orbit and these little recirculation zones. This is √3 over 2 epsilon, where epsilon was the strength of the quadrupole. So the steadily translating orbit is √3 over 2 epsilon above. That's the height above. But as epsilon tends to 0, which means you're forgetting about the quadrupole, this goes down to the origin. There isn't a steadily translating orbit. It's the combination of the stresslet and the quadrupole that allows the thing to move along. So that was something we learned from this. Yeah. Oh, and by the way, remember, I told you that in our swimmer model we had this. There was a 2 there. Then everything I did in the last couple of lectures was just this one, and that was the one that led to this. So you either had a steadily translating orbit, or you had these nonlinear orbits, which are one of these. But if you keep this in U non-zero and do exactly the same analysis, you get this kind of asymptotic stability process where it kind of equilibrates to a steadily translating state. It's almost like the U brings in a dissipative effect, but it's the self-propulsion. Right, what else? Yeah, and this was the fact that, you know, this was observed with spheres and rods. This is the graph you get. But if you replace spheres and rods with sperm cells, you get qualitatively the same thing. And we now know that if you replace sperm cells and spheres and rods with circular treadmillers with this velocity profile, you get the same thing. These are important lessons. It tells you that the details of the swimmer, a lot of the details are not important. It tells you that it's the far field multipoles that really govern the dynamics. Oh, so you see, look what happens. You see, this was with U not equal to 0. And what happens is this, when U is 0, this disappears completely. This is, for example, the swimmer being able to completely escape from the wall because it's got self-propulsion, so it can actually just, if it's directed in the right way, it will just go away from the wall if it's got some self-propulsion. But if there's no self-propulsion, you just have these types of behaviors, things getting trapped in these little periodic orbits. All right, and those were the experiments. Okay, so what I thought I'd finish with is I'm going to show you how you can use a lot of the same mathematics in a completely different area of investigation. So this is microfluidics. And this is a silicon chip. And in here, there's increasingly lots and lots of very dense electronic components, getting increasingly dense as we improve our technologies. But what it means is it's producing more and more heat. And in order to try to cool these, what people have done is they've made the tops of these chips, they put these little pillars and posts. Okay? Now, by the way, there's normally a top on here, and what you're doing is you're pushing liquid over these microchips with the hope that the heat will come up into the liquid and be transported away. It's a heat transfer problem. Okay? Now, here's the optimization problem. You see, this is a solid surface, a pillar. And so this is a no-slip region. these pillars are they're made of metal, usually, silicon, very good at transferring heat to the liquid. But they're no-slip surfaces. So if the whole thing was no-slip, it would be very, very hard to push the fluid through these tiny chips. That you need huge pressure gradients. You understand? So, I want to have these free surfaces here, or these slots. And these are free surfaces. And what happens is, because these are so small, surface tension is active here to allow a little meniscus to form between the pillars. Now, that's very good, because it allows the fluid to slip. So when you're pushing fluid this way, it slips over these, which means that the pressure gradients needed to push the fluid through are much smaller. But they don't transfer heat to the fluid as well, because it's now air. This is full of air. And here's the hot microchip down here. So the heat has to be transferred through air to the free surface now to get to the liquid. So can you see the optimization problem here? You want to have free surfaces so that the fluid slips easily. But if you have too much free surface, the heat that goes through to the liquid deteriorates. So you've got to find the right balance between having just enough free surface, but not too much. Everyone understand? By the way, if you Google this is called direct liquid cooling, and you'll see lots of websites now, magazine articles about how people are investing in this. There's startup companies all over the place because everybody's got their own way of doing this. They're trying to make money from Google. My colleague who visited me from Tufts last year, he had a grant from Google, which is all about, he's got some ideas about how to do this with liquid metals, which sounds expensive to me. But in any case, it's liquid and not air, some kind of liquid. Telling you a little bit about more. So, okay, so these are these microchannel flows. Just gives you an idea. This is the silicon wafer. This is still a kind of part of this, but now you've got this air trapped in these pockets and these menisci. So what happens? And there's actually a protrusion angle here, and that's very important too. The pressure difference between here and here determines what this curvature is, and that's another factor that comes in. That makes it very complicated because this is a free boundary now. So these are what we call unidirectional surfaces, where I'm looking down on it now, where you have basically silicon and meniscus, and you're passing a flow over it. And what the engineers try to measure is this. These are known as the slip lengths. So just imagine that you actually had a fully no-slip surface. So there's no little menisci. Then it would be no slip. So if you had a shear flow over it, it would vanish here by no slip condition. But you see, suppose that, if you looked on a microscope at this little surface, there were lots of little menisci, and far away it would just look like a surface. But now if you had a shear flow over it, it would be slipping over the surface because of the presence of the free surfaces, the little meniscus, very small scales. And what people are trying to do is to maximize this thing. Sorry, B should be lambda. They want to maximize this, so this is big. Because if you move that down and that one's on there, it means it's slipping more. Okay, so I've got two more slides to show you. And what I thought I'd finish with is to show you what's become a very famous paper in this field by Philip. I'm going to retrieve one of his results. I think it's John Robert Philip. I think the reference is on the next thing. But I told this story in my colloquium. Philip wrote a paper in 1972. And I'm going to solve the problem for you now, one of them. But he solved it in the context of porous media flows, because he was interested in porous media, flow through rocks. And in 23 years, up to year 2000, he got 5 citations for his work. Beautiful, beautiful paper, but he got 5 citations. I think one of them was his own citation of his own paper. So in 27 years, 27, 28, he got 4 or 5 citations. Nobody cared. But because of all these new applications, his paper has now got nearly 200 citations in the last 10 years. And it's because people have realized that exactly these boundary value problems that he solved there in a completely different physics are precisely the same ones that arise in these channel flows. Okay? And what happened was, I think the story is that Howard Stone or perhaps Eric Loger came across the paper, and then they referenced it, and then everybody realized what was in it. So it became famous, suddenly. Important lesson there. You know, always publish your work, because you never know if it might become famous, even in an area you know nothing about. Philip, unfortunately, has passed away now, so he doesn't know this. I'm sure he'd be thrilled. Anyway, here are 2 problems that he solved in this paper. So, and he used complex analysis, which is why I love this paper. And the great thing is, 40 years on, people don't know the techniques anymore. So they're reading his paper and they're quoting his results, but they don't know how to derive it. So here's one problem. These slots are coming out of the board. And these are the free surfaces, and the point is now, you've got pillars. These are the pillars. And what Philip is assuming is the contact angle is 0. So what it means is they're flat. Okay? And it goes on periodically. So the blue lines here are the blue lines there. The point is, on here, we've got no slip. And on here, we've got no shear. But it can slip. Remember, a free surface can't support any shear stress. A no-slip surface can. It's solid. You know, it's got stronger bonds. Nothing can slip over it, but it can support shear stress. Free surfaces can't. So it's a completely different type. That's why they call these mixed-type boundary value problems. So here's the mathematical problem. You want to have a shear flow over this periodic surface, which is no slip here, no shear here, no slip, no shear, no slip, no shear. And you want to see what the slip length is as a function of how large this slot is compared to the period window. Okay, that's the problem. So that's what we call the transverse problem, because remember, the slots are coming out, but the flow is transverse to the slots. Okay? Slots are coming out like that, but we're flowing over it. The other problem, if the slots are coming out like this, the other problem is to have a shear flow over it in the same direction. That's the transverse problem. The longitudinal problem. Okay? So now the flow is going into the board, but it's getting faster as you go up. Does everybody see? So imagine these slots. You can either have shear flow across them or along them. You following? Yeah? And by superposition, it's a linear problem. If you can solve those 2 problems, you can solve any angle over, because you just decompose in the 2 directions and add the solutions. What's very interesting about this problem, you remember my very first few minutes of lectures 2 weeks ago, I told you about F, G, and H. I told you that you can break down 3-dimensional Stokes flows into the search for 3 analytic functions, F, G, and H. Well, if you want to solve this one, this is a biharmonic problem. You have to find F and G. And it's biharmonic. If you want to solve this one, and by the way, there's no pressure gradient. So you remember I showed you this. You have to solve this problem for the for the velocity field into the board. If there's no pressure gradient, I think in my notes I have P, I think I have that. But if there's no pressure gradient, that's not there, and you're solving for a harmonic W, and so you can introduce what I called H, which is chi, which hasn't got a physical significance, but IW. So this is what we want this. And this is its harmonic conjugate. Doesn't have any physical significance. But I'm looking for an analytic function. Okay? So in Philip's problem, to find the most general flow over this surface, I need to find F, G, and H, 3 analytic functions. Okay, I've got about half an hour to show you how to do this one, the slightly easier one. We'll find H. Okay? Just to give you a flavor. Let me just, oh, here's his result, by the way. Here we go, look at this. Flows satisfying mixed no slip and no shear conditions. Very boring title. It was all about boring porous media flows. But it's got 165 citations in the last 8 years. And it's a theoretical paper with complex analysis. And that's because these results, engineers can check these results. And engineers love formulae like this. Because they know log, they know sec, and that delta's just some, delta's basically, you know, this ratio over this. They measure that, and they stick it in. All right, let's see if we can get that. I'm not going to do it how Philip did it. Yeah, we'll come back to this. Okay, so this is Philip's longitudinal problem. So here we go. It's periodic. Okay. And the flows into the board. And actually, it's just over the top. Okay. So, we've got del squared W is 0 in the fluid. Let's do red and blue. Red is no slip, blue is the slots. So what's W got to be on the red, on the no slip? 0. Because you don't want any velocity on the no slip surfaces. And the no shear condition, let me just tell you, is this. You need the normal gradient to be 0 on the no shear. And we want it to be periodic across the period window. Now, remember, we've got a shear flow over this. Okay, so as z tends to infinity, or rather as y tends to infinity, which just go up, we want w tends to y plus the slip length. So this is, I've set the shear rate to be 1. Okay? So this corresponds to, all right, so that's it. This is the, happy? See, in most problems, you would have just said, oh, it goes like y far away. Of course, in this problem, it does go like y far away, and then it goes like some constant is the next order, but that's that constant that we want. That's what the engineers want. So how do we find it? Okay, let's introduce complex potential. Introduce this h function. Which is chi plus IW. So in other words, it's the W is the imaginary part of some h. And we all know, by the way, that d chi by dx is dW by dy, and d chi by dy, these are Cauchy-Riemann. Remember? That's what I mean by the harmonic conjugate. So W is what we want, it satisfies this. Chi is its harmonic conjugate, the function that satisfies these Cauchy-Riemann equations. Right. Let's use the Cauchy-Riemann equations, actually, to help us see this a bit more easily. If dW by dy is 0, what does that tell us about chi on the slot? See, on the no shear slot, the W by dy is 0. So what does that tell us about chi? dW by dy is 0, which means the chi by dx is 0. And the slot is along the x-axis. So d chi by dx is 0 along the x-axis, which means that chi is a constant on the slot. You want to see? And without loss of generality, I can set it to be 0. So look at what my problem is now. I want W is 0 on there and there. And then I want chi is 0 on there. So another way of saying this is real part of H is 0 on the slot. Imaginary part of H is 0 on the no slip. Okay. Let me show you how I solve these. What I did is I used conformal mapping again. I'm going to take the unit disk in a zeta plane with 2 points, alpha and alpha bar, on the imaginary axis strictly inside the disk. And I'm going to define eta to be zeta minus alpha okay. So this point maps to the origin in the eta plane, and this point maps to infinity. Let's just see what else happens. Once zeta is equal to 1, look, let's look at the conjugate. Remember I just did this with the Cayley map. Well, I get 1 over zeta minus alpha bar, 1 over zeta minus 1 over alpha bar. You will see this. 1 over zeta minus alpha, 1 over zeta minus 1 over alpha. Which is taking conjugates and use the fact that zeta bar is 1 over zeta. Let's just rearrange that a little bit. Let's take out, from the top, let's take out a zeta squared alpha bar. And that's going to be 1 minus alpha bar zeta, alpha bar minus zeta. That's the top. And the bottom is very similar. Everybody see? These 1 over zeta squareds are going to cancel. I'm going to swap these around and swap these around, and that won't make any difference. I'm going to swap these around and swap these around, won't make any difference. And I'm going to move that 1 over alpha bar in there so that that won't appear, and I'll get a 1 over alpha bar there. So these go. This becomes, I'm swapping it around, it becomes zeta minus 1 over alpha bar, zeta minus alpha bar. And the same thing on the bottom, but with what do you notice about this? Look at this. This thing is precisely this thing. And this thing is precisely this thing. So this is 1 over eta. So what does the unit circle map to in the eta plane? It maps back to itself. But I'll tell you something, it doesn't map to the whole of itself. Eta maps to, well, let me do it down here. Eta maps to this. So let me, I guess I'll use, well, I think I need to use blue. Let me show you what happens. This top part, alpha, of course, goes to the eta is equal to 0. So it goes to the origin. And alpha bar goes to infinity. Now it turns out that the whole of the upper half plane goes to the whole of the interior of the disk. And that this one, I need to do it the other way, goes to the, oh, damn. I need to do it the other way. Okay? So this point goes to here. This point goes outside. And then this line goes to this line. So maybe I'll do that. Do I need to do that in red? Yes, I need to do that in red. So this line goes to this line. And then basically what happens is you go along here, it goes kind of on one side of this cut, and then when you trace back on the other side, it goes up around on the other side. So do you know what this is? This is like a circular arc Tchaikovsky map. Remember the Tchaikovsky was to a flat plate. This is very similar, except it's to a circular arc, a portion of the unit disk. Circle. I'm going to introduce one more conformal map. Everybody watch. The first two terms are exactly the same as these two. But this one's got zeta minus 1 over alpha on the top. I'm going to make that zeta minus 1 over alpha bar. And on the bottom, I'm going to put the other way. So in other words, I've inverted this one. Rodri knows what that is, because he's using that in his work. This is an example of a radial slip map, and in fact, on zeta is equal to 1, you can show using similar manipulations. I'll let you do it as an exercise. R bar isn't equal to 1 over R; it's equal to R. So do you know what this maps to under R? It maps to this. Real axis. Again, this maps to the origin. And this maps to infinity. But now, this circle, instead of mapping to this and coming back on itself, it maps to this and comes back on itself. I haven't checked. The one thing you're probably worrying about is how do I know it comes back on itself? These points where it comes back on itself are zeros of the derivative of these maps. And you can actually check by taking explicit derivatives of these that they have zeros, they've got 2 zeros on the unit circle. So they necessarily turn back on themselves twice. Okay? Now, I've nearly finished. By the way, I was an expert on, I've been advocating the use of conformal slip maps and the fact that we should think of them as building blocks for many, many years. This is what we call the circular, unbounded circular slip map, and this is what we call a radial slip map. And I wrote a review article a few years ago called Conformal Slip Maps in Applied Mathematics, and that's because I use them all the time. This is just one example. And what I'm going to do now is I'm going to let Z be, I think it's minus I log eta, and I'm going to let H be minus I log R. And I'm going to pick the branch of the log to be along here, and then actually that forces it to be somewhere along, I think it forces it to be along the same one. But let's look at what this one does. Okay. Well, let's write it like this: minus I log mod eta plus arg eta. So let's think about what happens when I'm here. This is eta. On the top of it, so that the argument is 0. So the argument is 0, and log, and this is 0. So I start at the origin. This is 0. Okay? And then what I'm going to do, let's suppose I go round the unit circle in the eta plane. So suppose I go around like this. Then log of mod eta is 0. This is 0 everywhere on that circle. But this goes from 0 to 2 pi. Going through a red zone, a blue zone, and back up to a red zone. Roger is smiling because he can see it's all working out. So in other words, I need colours, red and blue, as I go round the, let's move this down. As I go around the unit circle in the eta plane, I get red, blue, and red again. And of course, by the time I come all the way round, my argument is at 2 pi. Now I'm going to go in here, along the cut. Along the cut, round 0, and back along the cut. Now look at this. On this side of the cut, the argument of eta is 2 pi, and mod eta is going down below, is less than 1, and it's going into 0, which means that this is fixed at 2 pi. By the way, this is 2 pi. This is fixed at 2 pi, and this is becoming very, very small, but there's a minus sign. This is negative, and there's a minus sign, and it's purely imaginary, so I'm going up the side of the period window. So the side of the period window is that one. And then I'm off at infinity. I go round infinity, which is saying, okay, let's go across there. And then, of course, my argument now is 0. And I come down here, back to where I started. Everybody see how beautiful it is? Right? So these are the two sides of the period window, here and here. And this is the whole of the unit circle. But part of it's red and part of it's blue, because this red maps to this bit, but this blue maps to this bit. Let's look at this one. What's the only difference? What's the only difference, my friends? The only difference, everything's the same. Except when I'm coming around this red thing and meeting the blue thing, I suddenly go off in 90 degrees to where I was before. Remember, everything's conformal map. And then I come back down, and so basically what I get here, look, is the same as before. Red. Same as before, but now it actually goes up. It goes up there and down there. What do you see? See, so look, suppose I'm coming along here, which means I'm coming along here. But then I turn 90 degrees. And I go in towards infinity, which is going up here. And then I come back on myself. And then I continue on my way, so that was going in here and coming back on myself, and then I go back around on the red. And finish my job. Everybody see? Now everybody look, this is Z and this is H. Red is no slip. No slip. Where is red here? Because they correspond. It's when the imaginary is here. It's the imaginary part of H is 0. Which is what I want. But when I'm on the blue, which corresponds to the blue here, this is 0, and my real part remains 0 when I'm on the blue. Does everyone see? Finished perfect time. Did everybody see that? That's a geometrical understanding of what these functions are doing. Let's just check this. I haven't checked this yet. We need H. Remember, H is chi plus IW, so we need H to tend to, look, that goes to IY. H is an analytic function. So as y tends to infinity, H is going like the IY, but it's analytic, so the real part must be going like X. So this is going like Z plus lambda I. See? If W goes like I, that means H must be going like Z. Let's check if my solution here, because I'm claiming this is my Z and H written parametrically in terms of the zeta variable. I've already satisfied the boundary conditions on the slots and the no-shear slip surfaces. I need to just check infinity. But look, Z looks like, well, let's write it down. In terms of zeta minus alpha over zeta minus alpha bar, zeta minus 1 over alpha, zeta minus 1 over alpha bar. That looks like minus I log zeta minus alpha as zeta tends to alpha. And remember, alpha is the thing that goes to the origin, which goes to infinity. And H is minus I log zeta minus alpha over zeta minus alpha bar. The only thing that changes is this term. You swap it over. And then also, hence H goes like Z as Z tends to infinity. Let me just say that again. Going up to infinity, remember, was going into the origin here, which was alpha. And I've just looked at these, and as Z goes to alpha, look, there's a logarithmic singularity. So Z blows up. This is the most serious singularity. But the same is true of H, which means that H goes like Z as Z goes to alpha. Zeta goes to alpha, which is Z goes to infinity. So there's only one thing. We solved the problem. This is the problem. We only need to read off lambda. Let me do that. Let me do that as well. Look what I'm going to do. Watch me, everybody. Look, I want to get the Z part plus lambda. So how about I do this? How about I force the thing that appears in Z here, even though I'm writing H? other words, I'm going to put z minus 1 over alpha over z minus 1 over alpha bar. That's what appears in z. But this is what appears in h, so to correct it, I better multiply by that and multiply by the inverse of this. And what you end up with is zeta minus 1 over alpha bar over zeta minus 1 over alpha all squared. Everybody see? One of these cancels with one of these, and then it leaves me with the one I need. Everybody see? And then this property of logs is just z minus I log and this tends, as zeta tends to alpha, to z minus I log as zeta tends to alpha little o of 1. So guess what this is? That's the slip length. That's the slip length that we were looking for, and in fact, it's gone now. But if you rewrite this in terms of the other geometrical parameters from the mapping, you get log sec. Okay, so this is minus lambda. No, this whole thing with an, you know what I'm saying. This thing is compared with I lambda. Everybody see that? If you want to see more details, all of this is in the paper that I wrote a few years ago on longitudinal slip lengths. Or I did the transverse problem too. But this retrieves Philip's solution and generalizes it to any number of no-shear slots per period window. So I did it with the prime function. But the other thing is, I would like to say that this is a much more geometrical approach to the problem than Philip. And with that geometrical insight, it's much easier to see other things you can do. Although Philip did use conformal maps. He just didn't do it like this. He used what we call Schwarz-Christoffel maps. And in fact, slip maps are special cases of Schwarz-Christoffel maps. But I would argue, especially since I built the most general Schwarz-Christoffel map using slip maps as building blocks, that the slip maps are themselves the most important thing. You can often use them, like I've seen here, to construct much more complicated functions. This was in the longitudinal case. You can do similar things for the transverse flow, for the F and the G. And I did that in the same paper. And right now, by the way, if people are interested in talking to me while I'm here, right now I'm very involved in all of these things. In fact, at the moment, we're trying to generalize all of this to include heat transfer effects and protrusion angles that aren't zero. Because, of course, look, they're all flat here. They weren't protruding. And everything I said here becomes more complicated when you've got protrusion angles. But that's what we're working on now, among other things. Okay, that's about it. And I finished with 5 minutes to go, so we can all go home. Yes, and feel free to email me.